Let's talk about RAG systems from working prototypes to production-ready deployments. This is the second video in my production RAG series. In the first video, we built a complete RAG architecture from the ground up. We covered document chunking, vector embeddings, hybrid search combining dense vectors with keyword matching, cross-encoder re-ranking, and LLM generation. We added multi-layer caching, monitoring, and horizontal scaling as well. The system handles straightforward retrieval pretty accurately. This video addresses what happens when straightforward is not enough. We are going to cover 6 major areas today. First, advanced chunking strategies including a semantic chunking, hierarchical chunking, and contextual chunking. Second, query transformation techniques like rewriting, decomposition, and hypothetical document embeddings. Third, agentic RAG architectures where an LLM orchestration retrieval retrieves it dynamically. Fourth, knowledge graphs and how to combine them with vector search. Fifth, evaluation frameworks with component level metrics and LLM-as-Judge patterns. And finally, as sixth, we'll also cover production hardening, including access control, guardrails, and cost optimization. Each section targets a specific limitation of the foundational design and provides concrete architecture solutions. Let's quickly recap the V1 architecture that serves as starting point. The V1 system processes documents through a 6-stage pipeline. Documents get chunked using recursive text splitting. The algorithm prioritizes splits at section boundaries first, and then paragraphs, then sentences when chunks exceed the size limits. Each chunk gets embedded and indexed into a vector database using the HNSW for approximate nearest neighbor search. At query time, we run the hybrid retrieval. Vector search and BM25 keyword search execute in parallel. Reciprocal rank fusion merges the results, then a cross-encoder re-ranker scores query documents pair jointly, improving the precision. The top results become context for LLM generation. We added a multi-layer caching to reduce latency and cost. Query cache, embedding cache, and retrieval cache compound to provide substantial savings for workloads with repetitive queries. The architecture works well under certain conditions. For clean, well-structured documents and straightforward lookup queries, the system performs pretty reliably. But this architecture makes implicit assumptions. It assumes each chunk is semantically complete in isolation. It assumes a single retrieval pass surfaces all the required information. It assumes that all content is extractable text. It assumes that every query benefits from identical processing steps. When these assumptions hold true, the system works great. The key question is, when do these assumptions break down? Let's talk about where the V1 architecture breaks down. Understanding these failure modes is essential because each section of this video directly addresses them. The first failure category is context loss and isolated chunks. A chunk references the table above, but the table exists in a different chunk. Let's say a legal clause states that subject to section 4. But what if section 4 spans 3 separate chunks? Recursive chunking optimizes for size constraints, not semantic completeness. The second failure category is single pass retrieval limitations. A query like, let's say for example, how does 2024 pricing compares to 2023 and what drove the changes? This query will actually require 3 distinct pieces of information that may not share semantic similarity. A single top K retrieval pass cannot reliably surface all of them. The third failure category is format complexity. PDF extraction scrambles the tables, charts become disconnected labels, and multi-column layouts interleave unrelated paragraphs. The chunking pipeline assumes that clean text is there that real documents actually rarely provide. So we need to also consider all the edge cases. The fourth failure category is static pipeline inflexibility. Simple queries do not need query decomposition. Complex queries, however, they do need different strategies. In the V1 architecture, it processes everything identically, but in V2 video today, we'll explain how to address the other cases as well. The fifth failure category is quality measurement gaps. The V1 architecture we covered earlier, it monitors the tracks, the latency and errors, but not the retrieval relevance or generation faithfulness. Without component level metrics diagnosing the failures require actually manual investigation. So these 5 categories is what define what we need to actually solve, and this is what exactly we're going to look at in the V2 architecture in this video. Let's talk about the complete V2 architecture that addresses each failure mode we just discussed. The V2 architecture introduces adaptive components at every pipeline stage. This slide provides the map we'll reference throughout the video. The first major addition is the query transformation layer. Before retrieval begins, an LLM analyzes the incoming query. It may rewrite the query for better vocabulary alignment. It may decompose complex questions into subqueries. It may generate hypothetical answers to embed instead of the question itself. The transformation strategy adapts based on the query characteristics. The second addition is intelligent routing. A classifier or LLM inspects each query and routes it to the appropriate retrieval strategy. Factoid questions go to the vector search, analytical questions may trigger SQL queries, relational questions route to knowledge graph traversal, and some queries might actually need no retrieval at all. The third addition is agentic retrieval loop. Instead of fixed retrieval, then generate, an LLM agent actually decides dynamically what to retrieve, evaluates whether context is sufficient, and then it iterates if needed. The fourth addition is the knowledge graph layer. Entity and relationship extraction at ingestion builds a graph structure alongside the vector index. Graph retrieval traversal actually answers the relational queries that vector similarity cannot address. The fifth addition is multi-modal processing. Vision language models process the tables, charts, and images. And the sixth addition here is the continuous evaluation. Component level metrics track retrieval recall, re-ranking precision, and generation faithfulness separately. Now let's dive into the first major section, which is advanced chunking strategies. Let's talk about why recursive chunking, which served us well in V1, has fundamental limitations in production. Recursive chunking was a reasonable V1 choice. The algorithm is simple to implement. It produces predictable chunk sizes. It respects the document structure by prioritizing splits and natural boundaries. For well-structured documents with independent paragraphs, it works pretty effectively. Production corpora exposes the limitations. Let me walk through 4 concrete examples. First example would be, let's say, a financial report where paragraph 3 references the quarterly figures shown above. The table contains those figures were split into a separate chunk. The retrieved paragraph is relevant to the query but incomplete without the reference table. The second example would be, let's say, a legal contract where, let's say, a section 7.2a would state something like subject to the limitation in section 4. Now section 4 spans multiple pages and was split across 4 chunks. Retrieving 7.2a without the reference to limitations produces incomplete context. The third example is technical documentation where, let's say, a code example spans 40 lines. The recursive splitter hits its size limit at line 25 and splits it mid-function. The first chunk contains a function definition with no return statement. The second chunk contains a return statement but with no function context. And let's cover the fourth example where, let's say, a research paper where the methodology section uses the abbreviations defined in the introduction. Those definitions exist in the chunks that share no semantic similarity with the methodology content. Vector search won't be able to retrieve them together. The core issue is that recursive chunking treats size as a primary constraint. It does not model semantic dependencies between text spans. It does not preserve referential relationships, and it does not ensure that retrieved chunks are independently related and can be retrieved. Let's talk about semantic chunking, which uses embedding similarity to detect natural topic transitions. The core idea is pretty simple. Instead of splitting at arbitrary size limits, we identify where document meaning actually shifts. We let the content itself determine the boundaries. The process works like this. First, we split the document into sentences. Then we embed each sentence using the same model we use for retrieval. Then we compute cosine similarity between consecutive sentence pairs. High similarity indicates the sentences discuss the related content. Low similarity indicates a topic transition. When you plot these similarity scores, a pattern will emerge. Scores that remain high with coherent sections then drop sharply at the topic boundaries. These drops, these valleys in the similarity curve are where the semantic chunking places its splits. Implementation requires tuning a similarity threshold. Setting the threshold too high creates many smaller chunks, fragmenting the coherent sections unnecessarily. Setting it too low will create chunks that may exceed the context limits of mix the unrelated topics. The optimal threshold depends on your corpus characteristics and should be determined empirically by examining chunk quality on sample documents. The trade-offs are pretty clear. Semantic chunking produces more coherent chunks than recursive splitting. Retrieved chunks are more likely to be self-contained and interpretable. However, chunk sizes become variable and unpredictable, so some chunks may be very short if topic transitions happen frequently, Others may be very long if the document maintains a single topic. Ingestion cost also increases because every sentence now requires an embedding computation. Semantic chunking works best for narrative documents like articles, reports, and documentation where topic flow matters. It provides less benefit for highly structured documents like forms or tables where the structure is already defined with proper boundaries. Let's talk about hierarchical chunking. The fundamental insight is that retrieval and generation have conflicting granularity requirements. For retrieval, we want small chunks. Small chunks means embeddings capture specific concepts precisely. For generation, we want large chunks. Large chunks provide the surrounding context that makes specific passages interpretable. Hierarchical chunking solves this by storing the content at multiple granularity levels with explicit relationships between them. The implementation creates two chunk layers. Child chunks are small, typically a single paragraph or a few sentences. These are embedded and indexed for retrieval. Parent chunks are larger, typically full sections of multiple paragraphs. Each child stores a pointer to his parent chunk. At query time, retrieval operates on the child chunks. The small size means embedding captures the specific concepts pretty precisely. When a child chunk is retrieved, the system expands to its parent before sending the context to the LLM. The parent provides the surrounding context that makes a specific passage interpretable. Consider the earlier example of the table above, which was from the previous slide. So with hierarchical chunking, the child chunk contains the reference links to the parent chunk that includes both the paragraph and the reference table. The retrieval finds the specific relevant passage, and the expansion provides the reference content. Parent boundaries can be defined in multiple ways. Section boundaries work for well-structured documents. Fixed sliding windows work for unstructured content. Page boundaries work for the PDFs where the layout carries the meaning. One important detail to note is that deduplication matters when multiple children are from the same parent are retrieved. Without deduplication, the same parent content appears multiple times in the context, which will be wasting tokens. You should be tracking which parents have been included and try to skip the duplicates. Now let's talk about contextual chunking, an approach that uses an LLM to add document level context to each chunk before embedding. The core idea is pretty straightforward. For each chunk, we use an LLM to generate a brief preamble that situates the chunk within the full document. We prepend this preamble to the chunk text before embedding. The embedding then captures the document level context, not just the local text. The process works like this. For each chunk, we send the full document along with the specific chunk to an LLM. The prompt asks the model to produce a brief contextual summary explaining where this chunk fits in the document and what the key context from elsewhere is relevant. Then we prepend that summary to the chunk text, and then we embed the combined text. Here's a concrete example. A chunk that originally said, let's say, quote unquote, revenue increased by 12% this quarter, that might become, let's say, this section discusses Q3 2024 financial results for the North American division. Revenue increased by 12% this quarter. The embedding now captures that this is Q3 2024 North American and financial data. Queries about any of these dimensions will retrieve the chunk more effectively. Cost considerations are pretty important. This requires an LLM call for every chunk at the ingestion. For large corpus, this adds significant one-time cost. However, the cost is amortized across all queries. A cheaper, faster model can be used since the task is pretty straightforward summarization. Contextual chunking can be combined with hierarchical chunking. Use contextual preambles on child chunks, then still expand to parents at retrieval time. This provides both document level context in embeddings and extended context in the LLM prompt. Now let's talk about the handling complex document formats that break traditional text extraction. A real enterprise corpus contains PDFs with tables, multi-column layouts, embedded images, scanned documents, slide decks, and spreadsheets. Traditional text extraction produces unusable output for these formats. The solution is vision-based extraction. We send each page as an image to the multi-modal LLM. The model reads the visual layout and produces structured text output. Tables become markdown tables with proper row and column alignment. Multi-column layouts are then linearized correctly. Charts are then described with their data and conclusions, and handwritten annotations can be then transcribed. The approach is more robust than PDF text extraction libraries for complex layouts. Text extraction relies on the PDF's internal structure, which varies widely in quality. Vision-based extraction relies on visual interpretation, which handles arbitrary layouts pretty consistently. Table handling deserves a special attention. We should extract tables as structured data in Markdown or JSON format. You should be storing each table as its own chunk with metadata indicating its tabular data. Include the table caption and surrounding text that explains what the table contains. For scanned documents, the vision model handles OCR implicitly. No separate OCR step is needed. The model reads the text directly from the image, including handling for skewered scans and handwritten annotations. However, the trade-off is the cost. Vision model inference is more expensive than text extraction. Consider a tiered approach where simple text documents use the standard extraction and complex layouts use vision-based extraction. Document type classification can route the documents to the appropriate pipeline. Let's talk about how to choose the right chunking strategy for your corpus. Different chunking strategies suit different corpus characteristics. Here's a decision framework. For narrative documents with flowing prose such as articles, reports, and documentation, semantic chunking provides the best coherence. Topic boundaries naturally define the chunk pairs. Pair it with hierarchical chunking to maintain access to broader context. For hierarchical, highly structured documents such as legal contracts, technical specifications, and forms, structured aware recursive chunking works well. The document structure already defines the meaningful units, respect section, and clause boundaries here. You should be adding contextual preambles to capture the cross references. For mixed media documents containing tables and charts, you should be using vision-based extraction. The tables and figures they need visual interpretation. Text sections can use standard chunking after extraction. For long documents with extensive cross references, hierarchical chunking is pretty important. Cross references span beyond what any single chunk can contain, and parent expansion provides the necessary context. For knowledge bases with independent articles, simple approaches will be pretty sufficient. Each article is already a coherent unit. Recursive chunking within the articles handle the length constraints. One important point to note is that you can apply different strategies to different document types within the same system. You should route documents by type to the appropriate chunking pipeline and then store metadata indicating which strategy was used. Empirical validation is essential. Sample documents from your corpus, apply the candidate strategies, examine the resulting chunks manually, test the retrieval quality on representative queries, time the invested here will actually pay dividends throughout the system. And now let's move to the query transformation, which addresses a different set of problems. Now let's talk about why the user's natural language question is almost never the optimal retrieval query. The gap between user queries and optimal retrieval queries is one of the most underappreciated sources of RAG failure. The first issue is the vocabulary mismatch. Users and documents often use different terms from the same concept. A user can ask about, let's say, quote unquote, firing employees, but the HR documents discuss terms like termination, procedures, and workforce reduction. Vector similarity helps to bridge this gap, but this does not fully solve it. The query and relevant documents may embed in different regions of the vector space. The second issue is implicit context. Users assume context they don't explicitly state. For example, quote unquote, what is the policy? Assumes the context about which policy for which situation in which jurisdiction. The users know what they mean. The retrieval system, however, does not. Without that context, retrieval returns policies that might match on the surface features but might miss the user's intent. The third issue is multi-part questions. Complex queries require information from multiple sources that may not be semantically similar. Let's say, quote unquote, compare our approach to the comparator and recommend changes. This query will require finding our approach, finding comparator information, and then synthesizing a recommendation. A single embedding cannot capture all these three needs. The fourth issue is ambiguous references in conversational context. Let's say, quote unquote, what about the other option? This sentence will refer to something from early in the conversation. The query alone provides no information about what, quote unquote, what other option means. Query transformation addresses these gaps by modifying the user's query before the retrieval. The following slides cover specific transformation techniques. Let's talk about query rewriting, which uses an LLM to reformulate user queries into optimized retrieval queries. The implementation is a lightweight LLM call before the retrieval. The prompt provides the user's queries and asks the model to generate improved search queries. The model output becomes input to the retrieval system. Query rewriting addresses several problems. First, vocabulary alignment. The rewriter knows that quote unquote firing employees should also search for quote unquote terms like termination and workforce reduction. It expands the abbreviation and acronyms. It adds domain specific terminology that users may not know. Second is clarification expansion. If the user asks, let's say, quote unquote, what is the deadline? The rewriter might generate what is the project deadline for the current quarter based on the conversation context or user profile information. Third, multiple query when the user's intent is ambiguous, we can generate several interpretations, run retrieval for each, merge and deduplicate results. This increases the recall when the correct interpretation is uncertain. Latency impact is also a consideration. The rewriting step adds an LLM call before the retrieval begins. For latency sensitive applications, you should consider using a small, fast model. For simple queries where rewriting adds no value, skip this step entirely. A classifier can predict which queries benefit from rewriting. Not every query needs a retransformation. Specific, well formed queries with clear vocabulary can pass through unchanged. The rewriter should recognize these and avoid the unnecessary modification. Now let's talk about query decomposition, which breaks the multi-part questions into independent subqueries. Consider the question. Let's say, how does our 2024 pricing compare to 2023 and what drove the changes? This contains three information needs. First, what is the 2024 pricing? Second, what was the 2023 pricing? Third, what rationale explained the changes? A single retrieval pass cannot reliably surface all three. The decomposition process uses an LLM to identify distinct information needs and generate a subquery for each. The prompt asks the model to break down the question into independent searchable queries. Then we run parallel retrieval for all subqueries simultaneously. This minimizes the latency impact. Each subquery returns its own set of chunks. We merge the results, remove the duplicates, and assemble the combined context for generation. The generation prompt must handle the multi-part structure. You should provide clear definition of which context addresses which subquery. The LLM synthesizes across the separate evidence sets to produce a unified answer. Decomposition adds value for complex analytical questions, comparison questions, and questions with multiple explicit parts. It adds unnecessary overhead for simple factoid queries. Classifier can determine which queries benefit from decomposition based on the query structure and complexity signals. Let's talk about hypothetical document embeddings, commonly known as HyDE. HyDE addresses a fundamental asymmetry in retrieval. Questions and answers occupy different regions of embedding space. Questions are interrogative, and documents are declarative. Embedding a question and finding similar documents requires bridging the semantic gap. HyDE inverts the process. Instead of embedding the question directly, we use an LLM to generate a hypothetical answer. We embed that hypothetical answer and then we use it as a retrieval query. The hypothetical answer is declarative like the documents. Semantic search finds documents that resemble the hypothetical answer. Here's how it works. The user asks questions like, for example, what are the tax implications of stock options? The LLM generates a hypothetical answer explaining tax treatment based on its training knowledge. The hypothetical answer is then embedded. Retrieval finds documents that discuss similar content. Those documents contain the actual authoritative information. The technique works because the hypothetical answer exists in the same semantic space as the real documents. Even if the hypothetical answer contains error, its structure and vocabulary align with how real documents discuss the topic. However, limitations do exist. If the LLM generates a completely incorrect hypothetical answer, retrieval may find documents that match the wrong content. HyDE works best for factoid questions where the general shape of the answer is predictable. It's less effective for questions where the answer space is highly variable. HyDE can be combined with standard query embedding. Run retrieval using both the original query embedding and the HyDE embedding. You should then merge results. This provides a robustness when one of the approaches fails. Let's talk about building a complete query transformation pipeline that combines these techniques. Query transformation techniques are most effective when applied selectively. A pipeline that classifies queries and routes them to appropriate transformations outperforms applying all transformations uniformly. The classification step analyzes each incoming query. Simple factored queries pass through with minimal transformation. Complex multi-part queries trigger decomposition. Queries with vocabulary mismatch signals trigger rewriting. Queries where HyDE is likely to help trigger hypothetical document generation. Classification can use a lightweight model trained on query patterns. Features include query length, presence of comparison words, question type, and entity mentions. Alternatively, an LLM can classify queries using a few short prompts describing when each transformation helps. Multiple transformations can be decomposed. A complex query might be composed into subqueries with each subquery then rewritten for vocabulary alignment. The order matters. The decomposition typically comes first, followed by the rewriting of each component. My recommendation is to start with query rewriting. It provides the highest return for the broadest range of queries, and decomposition only when you identify query patterns that require it. You should add the HyDE approach selectively for query types where the evaluation shows it improves the retrieval. Measure transformation impact pretty explicitly as well. Compare the retrieval metrics with and without each transformation. Some transformations may actually degrade performance on certain query types. Disable the transformations for query categories where they hurt. Now let's move to the Agentic RAG, which represents the biggest architectural shift in this video. Let's talk about moving from static pipelines to adaptive agents. The fundamental limitation of V1 architecture is that every query follows the same fixed path. The pipeline does not adapt to what the query actually needs. Simple questions receive the same processing as complex ones. Questions that need no retrieval still trigger the full pipeline. Agentic RAG replaces the fixed pipeline with an LLM-powered agent. The agent dynamically decides what tools to use, what to retrieve, how to evaluate results, and when it has enough information to answer. The agent operates as a reasoning loop. It receives the user's query, it decides on an action such as searching a vector index, querying a database, or fetching a specific document. It observes the results, it evaluates whether the results are sufficient. If not, it decides on another action. The loop continues until the agent determines it can answer or has exhausted its options. This architecture provides the capabilities impossible in static pipelines. The agent can reformulate queries based on the initial results. It can retrieve from multiple sources and synthesize. It can recognize when the retrieved context is insufficient and can try alternative approaches. It can then decide that no retrieval is needed for certain queries. The trade-off is complexity and cost. Each agent reasoning step is an LLM call. A query that required one LLM call in the static pipeline may require 3 or 5 calls in the agentic system. Latency and cost will increase proportionally here. Let's talk about the router pattern, which is the simplest form of agentic RAG. A classifier or LLM inspects each query and routes it to appropriate retrieval strategy. Different query types go to different backends. Factoid questions about document content route to vector search. The standard retrieval, re-rank, and generate pipeline handles these scenarios. Analytical questions involving structured data route to SQL. Questions about counts, aggregations, comparisons, and trends often have answers in databases rather than documents. And relational questions route to knowledge graph traversal, which is the questions about relationships between entities, organizational hierarchies, and citation networks require graph queries. Conversation follow-up route to dialogue history. Questions that reference earlier conversation turns need that the context get included. Some queries need no retrieval at all. Greetings, clarification requests, and out-of-scope questions can be answered directly. Implementation can use a fine-tuned classifier for speed and low cost. Training data comes from labeled query examples. Alternatively, an LLM with a routing prompt provides flexibility without training. The router pattern captures much of the value of the agentic RAG with minimal complexity. Many production systems benefit from routing without needing full agent reasoning loops. Let's talk about giving the LLM access to retrieval as a callable tool. Tool definitions describe available retrieval capabilities. A vector search tool accepts query text, optional metadata filters, and a count of results to return. A SQL tool accepts a query string. A document fetch tool accepts a document identifier. Each tool definition includes a description of when to use it. The agent generates tool calls as part of its reasoning. When it needs information, it produces a structured tool call with appropriate parameters. The system executes the tool and returns results to the agent. The agent incorporates the results into its context and continues reasoning. This architecture enables the capabilities impossible in static pipelines. The agent can search for specific filters based on the query analysis. It can request more results if initial results are insufficient. It can combine results from multiple tool calls. It can decide mid reasoning that a different search strategy would work better. Compared to the static pipeline, in V1 the same retrieval parameters apply to every query. Top K was fixed, filters are predetermined, and the agent approach allows the parameters to vary per query based on the agent's assessment. Now, guardrails are pretty important. You should be limiting the number of tool calls per query. You should set the timeouts on the tool execution. You should be defining fallback behavior when the tools fail. And without the limits, agents can never enter the expensive infinite loops. Let's talk about self reflection, which enables the agent to evaluate whether retrieved context is sufficient before generating an answer. The implementation adds an evaluation step after the retrieval. A judge prompt asks the model to assess whether the retrieved chunks contain enough information to answer the user's question. The model outputs a judgment, sufficient, insufficient, or contradictory. If the judgment is insufficient, the agent enters a retry loop and analyzes why the initial retrieval failed. Perhaps the query terms did not match the document vocabulary. Perhaps the answer requires information from a different source. Based on this analysis, it reformulates the query and it retrieves again. If the judgment is contradictory, the agent retrieves the additional sources to resolve this conflict. If the judgment is sufficient, the agent proceeds to generation. Guardrails are what prevent the infinite loops. You should be setting a maximum retry count. Track which query formulations have been tried to avoid repetition. You should be defining a fallback response when retrieval repeatedly fails. The evaluation prompt requires careful design. It must distinguish between context that partially addresses a question, which may be sufficient for a qualified answer, and context that does not address the question at all. Overly strict evaluation triggers unnecessarily retries. Overly lenient evaluation passes through bad context. Let's talk about multi-hop retrieval, which handles the questions that require chaining information across multiple documents. Consider the question, quote unquote, let's say, what is the revenue impact of the policy change mentioned in the Q3 board demo? Answering questions like this require multiple hops. First, you should find the Q3 board memo. Second, it needs to identify which policy change it mentions. Third, it needs to find the revenue data associated with that specific policy change. Each step depends on the information from the previous step. The agent executes this as an iterative retrieve, read, query cycle. Initial retrieval finds the Q3 board memo. The agent reads the memo and extracts the policy change reference. A follow-up retrieval searches for revenue impact of the specific policy. The agent synthesizes the chain of evidence into a final answer. Multi-hop differs from query decomposition in an important way. Decomposition breaks a question into parallel subqueries that can run simultaneously. Multi-hop is inherently sequential because each query depends on the results from the previous step. Implementation requires the agent to maintain state across hops, what entities have been identified, what facts have been established, and what remains unknown. Latency accumulates across hops. Questions requiring 3 or 4 hops take proportionally longer. For latency-sensitive applications, limit the number of hops or provide progressive responses as each hop completes. Let's talk about the multi-agent architectures for complex systems. For sophisticated workflows, specialized agents handle different subtasks. A planning agent orchestrates them. The planning agent receives the user's query and decomposes it into subtasks. It assigns each subtask to appropriate specialist agent. It collects results and synthesizes the final response. A retrieval agent specializes in document search. It handles query formulation, retrieval execution, and result evaluation. A SQL agent specializes in structured data queries. It translates natural language to SQL, executes queries, and formats the results. A summarization agent condenses log documents or large result sets. A verification agent checks the claims against sources. This architecture is warranted for complex enterprise systems with diverse data sources and query types. However, most systems should start with single agent architectures using tools. Multi-agent adds coordination overhead and debugging complexity. Graduate to multi-agent when single-agent approaches demonstrably fail to handle your query complexity. Agent communication patterns do matter. Hub and spoke with a central planner is the simplest and you should be starting there. Let's talk about when to use Agentic RAG versus simpler approaches. Use static pipelines when query patterns are uniform, latency requirements are strict, cost per query must be minimized, and query complexity is low. The V1 architecture remains the right choice for many production workloads. Use routing when query types vary, but each type has a predictable retrieval strategy. Routing adds minimal latency and cost while enabling query appropriate handling. Use agent single agent with tools when queries require adaptive retrieval, when initial retrieval may not be sufficient, and or when the multiple information sources must be combined. Use multi-agent with when query complexity exceeds what single agent can handle. Common anti-patterns to avoid are over-agentification applies agent architectures to problems that static pipeline solves well. Infinite loops occur when the agents lack proper termination conditions. Excessive retries occur when the evaluation is too strict. Cost modeling is pretty important as well. You should be estimating LLM calls per query for each architecture option, multiplied by the expected query volume. Then you should be comparing that to your budget because agentic architectures that seem elegant may be economically unviable at scale. You should be also starting simple, add agentic capabilities incrementally as the evaluation demonstrates the value. And now let's move to knowledge graphs. Let's talk about the fundamental limitations of vector similarity retrieval. Vector search finds documents that are semantically similar to the query. It cannot answer questions that require understanding relationships between entities. Consider the question. For example, which suppliers have contracts with both company A and company B? Vector search will find documents mentioning company A and documents mentioning company B, but cannot perform the set intersection required to identify suppliers appearing in both relationship sets. Now consider the question, what is the reporting chain between the VP of engineering and the junior developer who filed the bug report? This requires traversing an organizational hierarchy. Vector search has no concept of hierarchy traversal. Now consider the question, which research papers cite both the Smith 2020 and Jones 2021? This requires understanding the citation relationships and finding the intersection. These queries require structured and graph-based retrieval. Entities exist as nodes with the properties. Relationships exist with edges with types. Queries traverse the graph structure to find the answers. Knowledge graphs complement the vector search. They don't replace it. Factoid questions about document content still benefit from vector retrieval. Relational questions require the graph traversal. Many real-world questions actually require both. Now let's talk about how to build a knowledge graph from a document corpus. Entity extraction identifies the mentions of people, organizations, products, dates, locations, and domain-specific concepts. Named entity recognition models handle common entity types. For domain-specific entities, fine-tuned models or LLM-based extraction perform better. Relationship extraction identifies how entities relate to each other. For example, John Smith is the CEO of Acme Corp. This establishes an employment relationship. Acme Corp, let's say, acquired Beta Inc. company in 2023. This sentence establishes an acquisition relationship with a temporal attribute. LLMs excel at their relationship extraction when prompted with entity pairs and surrounding context. Graph construction creates the nodes for entities and edges for relationships. Both do carry metadata. Entity nodes store the entity type, canonical name, and aliases. Relationship edges store the relationship type, conference score, and temporal attributes. Each node and edge links back to the source chunks. Now, the schema actually matters and it's pretty important. You should be defining which entity types exist in your domain. You should be also defining which relationship types connect them. A well-defined schema enables the precise queries. Now, deduplication is pretty important as well. The same entity may appear with different names across documents. For example, John Smith, J. Smith, the CEO might all refer to the same person. Entity resolution merges these into a single canonical node while preserving the alias for retrieval. Now let's talk about combining graph traversal with vector search. Hybrid retrieval runs both graph traversal and vector search, then merges the results. For each query, we classify whether it has relational components. Questions containing relationship words, entity references, and structural patterns suggest graph retrieval. We also classify whether it has content components. Questions asking about what documents say suggest vector retrieval. Many questions actually have both. Graph retrieval converts the query to a graph query. For, let's say, example, which suppliers work with both company A and company B? The graph query finds the supplier nodes with edges to both company nodes. The result is the set of entity nodes and the associated source chunks. Vector retrieval runs standard semantic search. The result is chunks ranked by the relevance. Merging combines both result sets. Chunks associated with graph retrieved entities receive a ranking boost. The boost magnitude is a tunable parameter. Not every query benefits from graph retrieval. Simple factored queries may receive no boost from graph traversal. A query classifier can determine when to activate the graph retrieval. Now let's talk about practical considerations for knowledge graphs at scale. Extraction cost scales with corpus size. Every document requires LLM calls for entity and relationship extraction. Strategies to manage costs include using cheaper models for initial extraction with expensive models for verification and incremental extraction that only processes new or changed documents. Graph maintenance as documents update require careful handling. New documents add nodes and edges. Updated documents may change relationships. Deleted documents require removing the associated graph elements. Community detection identifies the clusters of densely connected entities. The communities often represent the coherent topics or organizational units. Detecting communities enables the hierarchical summarization. Summary generation creates the text summaries for each community. These summaries describe what the community represents. This enables the global queries where questions about corpus-wide topics can retrieve community summaries rather than individual chunks. Evaluate whether the knowledge graphs are worth the investment for your use case. They add significant complexity and cost. They do provide unique capabilities for relational queries. So, if your query patterns rarely include relational questions, simple architectures may suffice. Now, let's move to the multi-modal RAG. Now, let's talk about extending RAG beyond the text to handle visual content. Real enterprise document collections contain far more than plain text. Financial reports include tables and charts, technical documentation includes architecture diagrams, legal files include scanned signatures, and presentations combine text, images, and layouts. Users ask questions that require understanding visual content. For example, they might be asking, what does the network topology diagram show? This requires interpreting the diagram. Or they can be asking, what are the values in the revenue chart on page 7, which requires reading the chart. Text extraction alone cannot provide these questions. The V1 pipeline extracts the text and discards the visual information. Tables become garbled and like rows that cannot be properly read. Charts become disconnected labels and diagrams disappear entirely. So now multimodal RAG actually integrates the visual understanding into the retrieval and generation pipeline. The challenges are distinct from the text RAG. How do we index visual content for retrieval? How do we retrieve images relevant to the text queries? And how do we incorporate visual context into LLM generation? So for this, two primary strategies exist. The first processes visual content at ingestion time, converting it into text descriptions. The second process visual content at query time, passing images directly to the multi-modal LLMs. Let's talk about using vision language models for document understanding. The process treats each document page as an image. We send the page image to multi-modal LLM. The prompt asks the model to extract all text content, convert tables to markdown format, describe the charts and diagrams, and note visual elements like signatures. The model output is structured text that captures the content traditional extraction misses. So, table retain the row and column structures, charts are described with their data points and trends, diagrams are explained with their components and relationships. This extracted text flows through the standard chunking and embedding pipeline. Retrieval operates on the text as usual. The text descriptions serve as the proxies for the visual content they describe. This approach works well for converting visual content to searchable text. Tables become retrieval based on their content. Chart descriptions match queries about trends and values. The limitation is information loss. The text description cannot capture every small visual detail. Subtle chart patterns may be summarized away. For queries requiring precise visual analysis, this proxy approach may not be sufficient. Cost considerations also favor this approach for large corpus. The vision model runs once per page at ingestion. The cost to amortize across all subsequent queries. Now let's talk about the multi-modal embedding models that enable the cross-model retrieval. Models in the CLIP family learn aligned representations. Training on image caption pairs teaches the model to embed images and their descriptions near each other in the vector space. A text query like network architecture diagram embeds near actual network architecture diagrams. Implementation adds image embedding to your index. Process to each image through the vision encoder to produce a vector. Store these vectors alongside text chunk vectors. Add metadata indicating the modality. At query time, embed the text query using the text encoder. Search across both text and image vectors. Results may include both text chunks and images. Filtering by modality enables the flexible retrieval strategies. Some queries should search only text, some should search only images, and some should search both. Limitations of current multi-modal embeddings affect the retrieval quality. Clip-style models capture the high-level semantic content but miss fine details. They recognize that an image is a network diagram but may not capture specific node labels. For queries requiring fine-grained visual understanding, pair the multi-modal retrieval with query-time vision model processing. Retrieve the candidate images using embeddings. Send the retrieved images to a vision LLM for detailed analysis. Now let's talk about the complete multi-modal architecture. At ingestion, documents are processed through format-appropriate extraction. Pages with complete complex layouts are sent to a vision LLM for structured text extraction. The extracted text is chunked and embedded. Important images are separately embedded using a multi-modal encoder. Links connect images to the source documents. At query time, both text and image retrieval run based on the query classification. Simple text queries search only the text index. Visual queries search both indexes. Results are merged and deduplicated. Generation uses a multi-modal LLM that accepts both text and image inputs. Text chunks are provided as usual. Retrieve images are then included directly into the context, and the model can reference both text and visual evidence. You should be starting with the vision-based extraction if your primary need is making a visual content searchable. Add multi-modal embedding and retrieval if the users frequently search for images directly. Add multi-modal generation if answers require synthesizing visual and text evidence. You should be evaluating which visual content in your visual corpus provides the retrieval value. Not every image needs indexing. Decorative images and logos may add noise without benefit. Now let's move to the evaluation, which is where the most production teams are weakest. Now let's talk about why evaluation is hardest problem in RAG. RAG systems have multiple components, each can fail independently. End-to-end metrics hide which component caused the failure. Consider a bad answer. The generation model may have hallucinated, or it may have faithfully summarized the relevant context. If context was irrelevant, the re-ranker may have ranked poorly, or it may have received poor candidates for retrieval. If the retrieval was poor, the query may have misformulated, or the relevant content may not exist in the corpus. End-to-end evaluation tells us the result answer was bad. It doesn't tell us why. Without knowing why, we cannot fix the problem. Improving the generation problem does not help if the retrieval is the bottleneck. Improving retrieval does not help if the re-ranker is discarding good results. Component level evaluation measures each stage independently. Retrieval metrics assess whether the retriever finds relevant documents. Re-ranking metrics assesses whether the re-ranker surfaces the best documents. Generation metrics assesses whether the model produces faithful answers from the provided context. Combining component level and end-to-end evaluation provides diagnostic power. End-to-end metrics detect the problems, component level metrics localizes them. Let's talk about evaluating retrieval quality. Retrieval evaluation measures whether the retriever finds the documents that should be found. This requires ground truth. For each test query, which documents are relevant. Recall at K measures what fraction of relevant documents appear in the top K results. If 5 documents are relevant and 3 appear in the top 10, recall at 10 is 0.6. Low recall indicates relevant documents are not being retrieved. Precision at K measures what fraction of top K results are relevant. If 10 documents are retrieved and 6 are relevant, precision at 10 is 0.6. Low precision indicates irrelevant documents are polluting the results. Mean reciprocal rank or MRR measures how high the first relevant results appears. If the first relevant document is at position 3, the reciprocal rank is 0.33. MRR averages this across queries. Building evaluation sets requires relevant judgments. For each query, annotators identify which documents are relevant. This is pretty labor intensive. Strategies to reduce burden include using LLMs to generate candidate labels for human verification and deriving answer relevance from existing question pairs. If retrieval recall is low, no downstream improvement can compensate. The relevant information never reaches the generation model. Retrieval evaluation should be your first diagnostic when your answer quality is poor. Let's talk about evaluating generation quality given the retrieve context. Generation evaluation isolates the LLM's performance given perfect context. We provide the gold standard context that definitely contains the answer. We evaluate whether the model produces a good answer from that context. This isolation matters for diagnosis. If generation quality is poor, even with the perfect context, the problem is the generation model or prompt, not the retrieval. Faithfulness measures whether the answer uses only information from the provided context. A faithful answer makes no claim beyond what the context supports. Completeness measures whether the answer addresses all aspects of the question. A complete answer does not omit relevant information present in the context. Relevance measures whether the answer actually addresses what was asked. And consciousness measures whether the answer is appropriately brief without padding. Human evaluation remains the gold standard. Annotators rate responses on each dimension using the defined rubrics. Human evaluation is expensive and slow. Automated evaluation LLMs provide scalable approximation for rapid iteration. Now let's talk about using LLMs to evaluate RAG outputs at scale. The judge model receives the question, retrieve context, and generated answer, and then produces quality scores. Common evaluation dimensions include faithfulness, which measures whether the claims are supported by context, answer relevancy, which measures whether the response addresses the question, context precision, which measures whether the retrieved context is relevant, and context recall, which measures whether the necessary information was retrieved. Judge prompts the define which eight dimensions precisely. For faithfulness, the prompt might ask the judge to identify each factual claim and determine whether the context supports it. Critical limitations affect the reliability. Position bias causes the judge to favor content appearing first. Verbosity bias causes the judge to prefer longer responses. Self-preference bias causes the models to favor outputs from their own family. Inconsistency means the same input may receive different scores across the runs. Calibration is essential before trusting automated evaluation. Sample evaluation cases, for example, have humans score them, have the LLM judge score them, and then compare. If correlation is weak, refine the judge prompts. Multiple judges can improve reliability. Having several models evaluate each case, aggregate their scores, disagreement flag cases that need human review. Let's talk about generating test data from your corpus using LLMs. The process samples chunks from your corpus. For each chunk, an LLM generates questions that can be answered from the chunk. The model also generates reference answers. The result is triples of the question, chunk, and expected answer. Diversity requires deliberate stratification. Sample chunks from different document types generate different question types, factoid, comparison, procedural, analytical. Vary the complexity. Without stratification, synthetic data skews toward easy patterns. Validation caches the generation errors. Not all generated questions are unstable from the source chunks. Filtering step removes the invalid triples. Human spot checks verify filtering quality. A key pitfall is circularity, where the same model generates and evaluates. If the generator has systematic biases, the evaluator may share them. Use different models for generation and evaluation. Difficulty distribution often skews pretty easy. So, for example, LLMs naturally generate questions with obvious answers. Real user queries actually include hard cases. You should be augmenting the synthetic data with adversarial question generation targeting the edge cases. Synthetic datasets enable the regression testing. After pipeline changes, run the test set and compare the metrics. Let's talk about continuous evaluation in production. Offline test sets capture the point in time performance. Production evaluation captures ongoing quality as queries, documents, and expectations evolve. Implicit signal reveals the user satisfaction without requiring explicit feedback. Query reformulation indicates the initial answer was insufficient. Conversation abandonment indicates the system did not help. Returning users indicate the system provides the value. Click through on citations indicates whether users find a source is useful. If users frequently check sources, they may be verifying suspicious claims. Follow up the question patterns reveal the answer gaps. If users consistently ask follow ups about the same topic, the initial answer is incomplete for that topic. Explicit feedback provides a direct signal. Thumbs up or thumbs down ratings require minimal user effort. Optional text feedback provides a richer detail. Feedback loops connect the evaluation to improvement. Poor ratings on specific topics indicate chunking or retrieval gaps. Consistent faithfulness issues indicate the prompt problems, and high quality outputs can seed the fine tuning database datasets. Longitudinal tracking detects the drift. Quality metrics stable over weeks but declining over months may indicate corpus changes or model degradation. Now let's talk about verifying whether the generated answers are grounded in retrieved context. Claim decomposition breaks the answer into atomic factual claims. The statement, let's say for example, quote unquote, revenue grew 15% Q3, driven primarily by enterprise segment, contains multiple claims. Each requires a separate verification. Natural language inference models classify each claim against the context. Classification outputs are supported, contradicted, or neutral. Supported claims have explicit evidence, contradicted claims conflict with the evidence, and the neutral claims have no evidence either way. Neutral claims are tricky. The context may simply not discuss the topic, or the claim might be hallucinated. Conservative approaches flank the neutral claims for review. Citation generation pair claims with the specific source passages. The model outputs not just the answer but which chunks support each claim. Pipeline integration options include post-generation filtering, where ungrounded answers are blocked or regenerated, where rewriting, where the model revises the removing ungrounded claims, and user-facing indicators, where your confidence scores accompany the uncertain claims. Now let's move to the fine-tuning. Now let's talk about why fine-tuning matters for RAG systems. Off-the-shelf models are trained on general-purpose data. Your domain has specific vocabulary, writing styles, and information patterns. Fine-tuning bridges this gap. Three components cannot be fine-tuned. Embedding models learn better representations for your domain. Rerankers learn domain-specific relevant signals. And generated LLMs learn domain-appropriate response patterns. Embedding the fine-tuning improves the retrieval recall. If relevant documents exist but retrieval fails to find them, domain-adapted embeddings help. Re-ranking fine-tuning improves the precision. If retrieval finds the relevant documents but they rank too low, domain-adapted re-ranking helps. Generator fine-tuning improves the answer quality. If retrieve context is good but generated answers are poor, domain-adapted generation helps. Start with evaluation to identify your bottleneck. Fine-tune the component that most limits the quality. Fine-tuning the wrong component yields no improvement. Let's talk about fine-tuning embedding models. Training data consists of query passage pairs. Positive pairs contain a query and a passage that answers it. These come from existing question answer logs, synthetic generation, or manual annotation. Hard negative mining is crucial. Hard negative cases are passages that are semantically similar to positive passages but don't answer the query. Training on hard negatives teaches the model to make fine distinctions. Mining hard negatives uses the concurrent embedding model. For each query, retrieve the top passages, remove the true positives, and the remaining high-ranked passages are hard negatives. Contraceptive training objections push the positive pairs together and negative pairs apart. The query embedding should be closer to its positive passage than to any negative. The Matryoshka representation learning produces embeddings useful at multiple dimensionalities. The same embedding can be truncated to lower dimensions while preserving the quality. This enables trading storage against the quality without retraining. Evaluate on a held out query set. You should be compare the retrieval metrics before the end and the after. Let's talk about fine-tuning Rerankers. Training data requires query document pairs with relevance labels. Binary labels indicate relevance or not. Graded labels indicate highly relevant, somewhat relevant, or not relevant. Cross-encoder training requires fine-tuning a model to score query document pairs jointly. The model sees both texts concatenated and outputs as a relevant score. Hard negatives matter here too. So documents that appear relevant but aren't teach the model the subtle distinctions. Re-ranker fine-tuning often shows larger gains than embedding fine-tuning when the retrieval already retrieves a reasonable recall. The re-ranker is a mere precision filter here. Teaching a domain-specific relevant signals directly improves what teaches the LLM. Let's talk about fine-tuning the generated LLM. Training data consists of question, context, answer triples. The question is what the user asked, the context is retrieved chunks, the answer is the ideal response. Negative examples are pretty important. Include the examples where the context is insufficient and the correct response is to acknowledge uncertainty. Without these, the model learns to always generate answers even when it should abstain. Include the examples of proper citation. The answer should reference which chunks support which claims. Refusal training teaches when not to answer. Provide examples for auto-scope questions about appropriate refusal approaches. So the training typically uses supervised fine-tuning on the curated dataset. For stronger alignment, preference tuning methods can further improve the response quality. Now let's move to the production hardening. Now let's talk about access control, which most tutorials ignore, but production systems do require. Enterprise deployments require that users only access documents that they are authorized to see. Document level permissioning attaches the access control metadata to each chunk. Retrieval queries include a permission filter. Only chunks the user can access are returned. Implementation requires syncing permissions from your identity system. When the documents are ingested, extract the permission metadata. When the permissions change, update the metadata. Multi-tenant architectures add another dimension. Two approaches here exist. Shared index with tenant filtering stores all tenants into one index. Each chunk has a tenant identifier. Queries include a tenant identifier, and this is operationally simpler but carries data leakage risk from filter bugs. Isolated indexes give each tenant their own index. No filtering is needed here. This is more secure but more expensive. You should be choosing based on your risk tolerance. Test permission enforcement explicitly. Create the test users with different permission sets and verify that they can only access the appropriate content. Talk about keeping your index fresh without full rebuilds. Chain detection identifies which documents are new, modified, or detected. File hashes detect the content changes. Timestamps detect the modification times. For database sources, change the data capture provides a stream of modifications. Selective processing handles only changed documents. New documents flow through the full pipeline. Modified documents have old chunks removed and new chunks added. Deleted documents have chunks removed. Index updates without full rebuilds require the database support. Most vector databases support incremental operations. Cache invalidation ensures the cached responses reflect current content. When the documents change, invalidate the cache entries that may have included in those documents. Freshness versus latency trade-offs do exist. Near real-time updates keep the content fresh but add complexity. Batch updates with hourly or daily cadence are simpler but introduce staleness. Let's talk about protecting the production systems against misuse. Input guardrails screen the user's query before processing. Prompt injection detection identifies the manipulation attempts. Topic boundary enforcement rejects out of scope queries. PII detection flags the queries containing personal information. Prompt injection through retrieval context is a distinct threat. An attacker could insert malicious instructions into the documents. When retrieved, these instructions attempt to override a system behavior. Defenses include content scanning at ingestion and instruction hierarchy that prioritizes the system prompts. Output guardrail screen generated responses. PII filtering removes the personal information. Content policy enforcement rejects the violating responses. You should be balancing safety against usability. Overly aggressive guardrails block legitimate queries. Insufficient guardrails will expose the risks. Monitor guardrail triggers to fine-tune your thresholds. Now let's talk about optimizing end-to-end latency. Embedding latency depends on model size and inference infrastructure. Embedding caches eliminate the latency for repeated queries. Retrieval latency depends on index configuration. HNSW parameters trade accuracy for speed. Lower EF underscore search values query faster with lower recall. Re-ranking latency scales with the candidate count. Re-ranking 100 candidates takes proportionally longer than 20. Distal re-rankers are smaller and faster. Generation latency dominates the most pipelines. Streaming generation shows tokens as they arrive, improving perceived latency, caching common responses, and limiting the generation entirely. Parallel execution reduces end-to-end time when steps are independent. Query transformation, embedding, and some retrieval steps can run concurrently. You should be measuring latency at each stage. Percentile metrics matter more than the averages. P95 and P99 reveal the worst-case user experience. Let's talk about managing cost at scale. Embedding generation cost augmentation strategies include using smaller models, batching requests, and only re-embedding the changed content. Vector storage costs scale with vector count and dimensionality. Binary quantization reduces the storage dramatically. Lower dimensional embeddings reduce the storage but may reduce quality. LLM inference costs dominate the per query cost. Strategies include using cheaper models for simpler tasks, caching responses, and reducing the context length and generating shorter responses. Model routing reduces the cost. A classifier determines query complexity. Simple queries uses cheaper models. Complex queries uses more capable models. You should be building cost models at different scales. Cost per query at current volume. Cost at 10 times the volume. Some components may scale linearly. Others may have to have step functions. Now let's talk about monitoring that goes beyond system health. Request tracing captures every step of each query. The trace includes the original query, transformations, retrieval results, and generated response. Traces enable debugging. Retrieval quality metrics aggregate across queries, average retrieval scores over time, and percentage of queries with high confidence results. Generation quality metrics require automated evaluation, sample production queries, and run them through the LLM judges. Track the faithfulness and relevance scores over time. User satisfaction signals provide the ground truth. aggregate the ratings, track the reformulation rates, monitor the conversation completion rates. Alerting on quality degradation enables a proactive response. You should be setting thresholds for each metric, alert when the thresholds are crossed. List for our V2 systems. For document processing, have you evaluated chunking strategies? Have you implemented hierarchical or contextual chunking? Do you handle complex formats? For query understanding, have you implemented query rewriting? Do you decompose complex queries? For retrieval, is routing sending queries to appropriate backends? Can your system handle the multi-hop reasoning? For evaluation, do you have component level metrics? Have you validated automated evaluation? Do you have synthetic test sets? For access control, does retrieval enforce permissions? Have you tested the enforcement explicitly? For operations, you should check that is incremental indexing maintaining the freshness, are guardrails protecting against misuse, is latency within the budget, and is the cost sustainable? You should be prioritizing based on your failure modes. If retrieval is the back bottleneck, focus there first. Let's revisit the complete video architecture now that we have covered every component. Ingestion processes documents through format appropriate extraction, semantic or hierarchical chunking, contextual enrichment, and multi-modal handling. Entity extraction builds the knowledge graph, embeddings populate the vector index. Query understanding transforms the user's query before the retrieval, rewriting aligns with vocabulary, and decomposition handles the complex questions. Routing directs the queries to appropriate retrieval strategies, vector search, graph search, traversal, or SQL. Agentic retrieval enables the adaptive iterative search. The agent evaluates results and reformulates when it's needed and performs the multi-hop reasoning. Generation produces the answers from assembled context. Evaluation verifies faithfulness. Guardrails and ensures safety. Monitoring provides the quality focused observability. Component level metrics localize the problems. This architecture represents current best practice. Not every system needs every component. Implement incrementally based on your specific failure modes. Now let's talk about the maturity model for incremental adoption. Tier 1 is enhanced V1. Add contextual chunking, add query rewriting, implement the component level evaluation. These additions provide the meaningful improvement with modest effort. Tier 2 is adaptive. Add routing, add agentic retrieval, implement the knowledge graphs if relational queries matter, fine-tuning embeddings. Tier 3 is full V2. Add multi-modal processing, implement the multi-agent architectures, build continuous evaluation with feedback flywheels. Match maturity tier to use case requirements. Internal tools can succeed at Tier 1, customer-facing products near Tier 2, and mission-critical systems near Tier 3. Progression should be evaluation-driven. Measure the quality, identify the limiting component, implement the capability that addresses the limit, measure the improvement, and repeat. Avoid premature optimization. Implementing Tier 3 when Tier 1 suffices and is pretty sufficient will waste resources, so you should totally depends on your use case.